suppose u1, u2, un are, so if these are subspaces of V, then u1 plus u2 plus da 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 un is written as u1 direct sum, u2 direct sum, if any element in any vector in u1 plus u2 in is written uniquely as u1 plus u2 un with the ui being in capital U. And such a thing is called a direct sum. We've had two examples before, so let me write those examples again. I shouldn't have erased them. So one was u equals to x, x, y, y, x, y in R, and v equals to x, 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 y with x, y in R. And in this case, u plus v is not a direct sum. This capital, not a direct sum, because, well, we know. Just let's pick any element. What's in the u plus v? Can you recall what's in there? 1, 1, 2, 3. How's that? Yeah. That's in here, right? Well, we know that this is in here. That's something that we worked on in the previous example. But this can be written as, say, 1, 1, 1, something plus 0, 0. Sorry, this should be something, something, 0, 0, 0. Oh, 2, 1, 1, 2. And then it should be 2, 1. How's that? This is definitely in U, this is definitely in V. There's another way to choose this. What if I choose 1, 1, 1, I don't know, something. In this case, what should I choose for here? 0, 0, right? If I choose 0, this has to be 0. Now 1 plus what is 2? 1. So this must be 1. In order for this to be in here, this must be 0, 0, 1, 1, right? Okay. And then 1 plus what gives you 3? This must be 2. Okay. Oh, so now you see that this is in here, this is in here. So we managed to write this single object, single element in U plus V as sum of an element in U and element in V in two different ways, right? So this is not unique, therefore this is not a direct sum. Okay. In fact, there will be homework questions that ask you to prove that. Here's blah 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 blah. Show that these two are not a direct sum. Okay? And you show it by finding two different ways to write the same thing. Now, however, example 2, we had this other one where u is equal to x, 0, 0, right? And v is equal to now in this case, what's inside u plus v? We wrote down that this everything that's in here, they all like x comma t, right? But x comma t, how do you write it as an element from here and there? There's only one way to write it, right? Right? There's no other way to write it. The only way you can write this as an element from here, an element in here, is this. I mean, you can, if you still don't agree, we can make an argument for it. See, if you want this to be this plus something from here and there, anything from here, okay. But if who makes an argument with your girlfriend or boyfriend and always win? Like, I always win the argument against my girlfriend. Raise your hand. How about I always win my argument against my boyfriend? No? Okay. See, being good in math means you can win arguments, okay? But you always have to make sure that your arguments are sound, right? Yeah. But that kind of makes me wonder why I always lose my argument against my wife. But anyways, see, if you want to do well in proofs, you have to think about the case when there's this hypothetical stubborn person who would never give in to your argument. How do you make sure that you can show, you can like 100% clear prove something? And well, see, anything in here, if you have any vector in here, then v must look like some a, b, b. Do you agree? Right. And then if this was in something in here and there, let's say w for this, w. If it's from u plus v, where u is from here and v is from here, then u better look like x comma 0 comma 0, and then v better look like 0 comma t, because these are from here, right? But then if you add them up, what do you get? You get x comma t. For these two to be equal, you don't have any choice. X has to be a, right? And then t has to be b. There's no other choice, right? So uniqueness is proved. You're forced to say that, okay? So that's it. Is that clear? Okay. All right. So that's what it means to be a direct sum. Now, direct sums are later used. See, everything that we learn, I mean, there's some other minor things that are important, but most of the things that we learn, we are like trying to go towards this grand theory, which is the Jordan normal form or Jordan canonical form. It's like how far can you diagonalize? Not all matrices can be fully diagonalized. And there's some people Jordan canonical form that's like almost possible to diagonalize. And these kind of notations like direct sum is pretty important in getting there. Okay. All right. So let me put a theorem. There are two important theorems here. I have to write down the number for it, 1.44 in the textbook. So if you're 1.44 in the textbook is that u1 plus un is a direct sum what do I mean by IFF?
If and only if.
If and only if. If and only if 0 is uniquely written as u1 plus u2. These are lowercase. Okay. Proof. Well, if it is a direct sum, that means any vector including 0 is uniquely written. Right? Since any vector includes 0, 0 is also uniquely written, so done. That part is easy. Now, if and only if means that you have to show two different cases. So if it is a direct sum, then we know that 0 is uniquely written. Now, let's show that this case. Now, this case means that 0 is uniquely written as something in here. If that's true, then we know that this is a direct sum. That's what we have to show. Now, again, a lot of times what's given is not readily available for use, so we have to think about what this means. How can you represent 0 as a sum of different vectors? If it's a unique way, there's only one way to do it. What would be the what would each of these be? Zeros, right? So since 0 is equal to 0 plus 0, right? With 0 in each one of these UIs, right? 0 is in any subspace, that's given. Okay? And this is unique. In other words, there's only one way to write 0 as sum of elements from these subspaces. What does that mean? We see that 0 equals to u1 plus u2, un with uk and uk. So each one of these are in ui, in the subspace, implies u1 is 0, u2 is 0, un is 0. Wow, that's actually a pretty powerful thing. It means that anytime you can see 0 equals to a bunch of vectors from each of the subspaces, then in subspaces, then every one of these vectors must be 0. That's a pretty powerful thing. So we're going to use this. Use that. How do we use it? Well, now let's try to prove that this is a direct sum. Well, how do you show that that's a direct sum? Suppose V is in u1 plus un, so that V is equal to u1 plus u2 un. I want to use this, so let me rewrite it. Let me use V1, okay? Where VK is in VK, UK, sorry. UK. equal to W1 plus W2 Wn. Again, where Wk is in Uk. What do I have to show to say that V has a unique representation as sums of vectors in the subspace?
W1 must equal to V1, or Wi must equal to Vi for...
Yeah. So V1 has to be same as W1, V2 has to be W2. I need every one of these to be equal to each other. If that's true, then these two are not distinct, so they're exactly the same. That's what it means, right? Okay. So no matter how you try to write a single vector in two different ways, you will find that you end up writing the exact same vector. That's what I'm saying. Okay. In some proofs, you should just be able to do it. Okay. By thinking about each and every detail of what the conditions mean. Okay. However, from some proofs, you have to learn the method of proof. See, we've used this word uniquely. That's an English word, right? Now, when you write down the proof, you have to think about, wow, how do I represent that in math? How do I say something's unique in math? Well, the right way to do it, and this is the real lesson of this proof, is that if you write it in two different ways, you have to show that each of these individual terms end up being exactly the same. That's how you show something's unique. Is that good? All right, good. So let's try to prove it. Okay. Then, do you kind of see where I'm going with this? How would we finish this proof? How do I use this?
Subtracting.
You subtract and that's it, right? So then V minus V on one hand is V1 plus Vn minus W1 plus Wn, right? V minus V, in math you can substitute any one thing by another if they're equal. So since V is same as that, I replace this V by this. And since V is same as this one, I replace V by this other one. But then, I can simplify this. What's V minus V? 0. And I can rewrite this as V1 minus W1, V2 minus W2, Vn minus Wn. Right? Now, each Vk minus Wk belong to Uk. That's because this is equal to Vk plus -1 times Wk, right? So if Wk is in Uk, -1 times Wk is in Uk. If two things are in if both of these are in Uk, then their sum is in Uk. So we know that this is true, and because of that, we can apply this theorem, okay? And say the conclusion is that V1, so we're applying this theorem with U1 being this guy, U2 being this guy, and Un being this guy. What's your conclusion? Each one of these must be 0. So that's the proof. (1.45) U1 U2 U1 plus U2 is a direct sum if and only if U1 intersect U2 is 0. Okay. So let's prove this. First, let's go this way. here you're saying that u1 plus u2 is a direct sum, okay? Means that 0 is equal to u1. Oh. Sorry, let's not do it this way. So, to prove this is direct sum, that means this is this, we should say something else, okay? So, suppose not. So, that means there exists then there's a u in u1 and u2 with u non-zero. Something that I forgot to say, I think I skipped in the textbook, is that this is a subspace. Intersections are always a subspace. Unions are not, okay? So this will always be a subspace. Thus, negative u is also in u1 intersect u2. Because it's a subspace. Now, if you don't like that, you can use this. This means that u is in u1 and u is also in u2. Because this is a subspace, the inverse elements exist as well, right? So negative u is also in u1, negative u is also in u2, so negative u is in the intersection as well. Okay. Then 0 is equal to u plus negative u equal to 0 plus 0. Now this is not good because, look, u is in u1, right? 0 is also in u1. Negative u, so this also means negative u is in u1 and negative u is in u2. So this is in u2, this is also in u2. So I was able to write down 0 in two different ways, right? With one guy in u1 and the other guy in u2, right? So that means this contradicts u1 plus u2. The fact that u1 and u2 is a direct sum, okay? So that's the proof that way. Now since we're doing if and only if, we better do the other way. So suppose this way. So if u1 intersect u2 is 0, I have to show that u1 plus u2 is a direct sum. Well, we know that we can show this if 0 is uniquely representable, right? So let's say 0 is u1 plus u2 with u1, u2, u1 and u1, and u2 and u2. Well, then u1 is equal to negative u2, right? You can subtract u2 to the other side and you get that. So that u1 is also in, so that means negative u2 is in u1 as well. Because u1 is same as negative u2, so since u1 is equal to negative u2 is in u1 as well. But then we know that u1 is a subspace, so that means u2 is also in u1 as well. Being a subspace means that the inverse exists, right? But now look at this. That means that U2 is now in both U1 and U2 is in U2, which means that U2 is in the intersection of both, which has only one element, right? So what does that mean? U2 must be 0. Since U2 is 0, U1 is 0 as well, because it's negative of 0. Oh, so what did I show? I showed that 0 is, each of these are zeros, and that's the only way you can write down 0 with this given condition. So, because by 1.44, U1 and U2 is a direct sum. So that's how you prove it.